Welcome to the first presentation of this video playlist about the best methods for acylating alcohols to prepare carboxylic esters. In this part, we first have a short review of the use and industrial manufacturing strategies of carboxylic esters. Then I'll show you some examples of the use of acyl halides, mostly acyl chlorides, as electrophiles for preparing esters and of potential side reactions. The remaining presentations are about other electrophilic acylating reagents, about in situ activated carboxylic acids, and about the acid-catalyzed esterification of carboxylic acids. Finally, the acylation of alcohols with carbon monoxide and the oxidative acylation of alcohols with aldehydes will be discussed in part 5 of this video playlist. Carboxylic esters are useful compounds for a number of different applications. One important field is their use as solvents for paints, coatings, adhesives, inks, or various cleaners. For this application, esters with low boiling points, low toxicity, and a short environmental half-life are preferred. A further important group of esters are polymeric esters and the monomers required for the preparation of these polymers. Polyesters are used in textiles, for food packaging, and as coating for wood and other materials. Although simple, low molecular weight esters are readily saponified by aqueous bases, polymeric esters are much more resistant to chemical degradation. Some esters are also valuable high-temperature lubricants for various types of machines. Some polymers are too brittle for most applications and require a so-called plasticizer to improve their mechanical properties. Esters of phthalic acid are important and widely used plasticizers. Parafilm, for instance, contains dibutyl phthalate, which is readily extracted by chloroform or other solvents and may end up in one's product if parafilm is used to seal NMR tubes or other containers. The aroma of many plants and their flowers and fruits is caused, among others, by various carboxylic esters. Highly purified esters with boiling points below 250 degrees Celsius are therefore important ingredients in perfumes and synthetic flavors. Esters are also used to improve the properties of personal care products such as soaps, shampoo or lipsticks. Here's a small selection of some commercially relevant esters that are used as solvent, as monomer for the production of polymers, as plasticizer or as synthetic intermediate. The most important classes of monomers are vinyl esters, acrylates, and dicarboxylic acid esters. In vinyl esters and acrylates, it is the alkene which undergoes polymerization, initiated by radicals, acids, or bases. Diesters are polymerized by base-catalyzed transesterification with a diol at high temperature, usually above 200 degrees Celsius. Most large-scale preparations of esters are acid-catalyzed condensations of carboxylic acids with alcohols, or the addition of acids to alkenes, because no waste or only water are produced as byproduct. Vinyl esters can be prepared by the addition of acids to alkynes, by the oxidative coupling of acids with alkenes, or by acylation of aldehydes. Some carboxylic esters can also be prepared by disproportionation of aldehydes, as for instance under the conditions of the Tishenko reaction. Gamma-butyrolactone is a synthetic intermediate for the preparation of the solvent NMP and the monomer vinylpyrrolidone. Butyrolactone can be prepared from benzene, butane or butene by oxidation to maleic anhydride followed by partial hydrogenation. Alternatively, it can also be obtained from butanediol, which in turn results from the hydrogenation of butenediol. One further industrial synthesis of esters is the Celanese liquid phase oxidation of butane. This reaction yields mixtures of acetic acid, its methyl and ethyl esters, and some ketones, which can be separated by distillation. Carboxylic esters can not only be prepared by acylating alcohols, but also by a number of alternative strategies. Depending on the precise target ester and the required amounts, some alternative strategies may be more convenient than alcohol acylation. One alternative is the electrophilic alkylation of carboxylic acids. suitable electrophiles include alkenes and alkynes, alkyl halides or sulfonates, diazoalkanes, epoxides, and trialkyl oxonium salts. This strategy is best suited for acid-sensitive acids. Another strategy is the alkoxycarbonylation of organometallic intermediates with carbon monoxide. This reaction is discussed more thoroughly in part 5 of this video playlist. Carbon monoxide can also react with carbocations to yield acylium cations, which are strongly electrophilic acylating intermediates. Esters can also be prepared from ketones by treatment with a per-acid, or from nitriles by hydrolysis in the presence of an alcohol, usually under acidic conditions. Acetals and hemiacetals are good hydride donors and easy to oxidize. Thus, aldehydes in the presence of an oxidant are a further type of reagent that can be used to acylate alcohols. Some examples of this reaction are discussed in part 5 of this playlist. Finally, one further alternative ester synthesis is the reaction of polar organometallics such as organolithium or Grignard reagents with chloroformates or carbonates. Carbon monoxide cannot be used to convert polar organometallics into carboxylic acid derivatives because the intermediate acyl anions are highly reactive and are either not formed at all or yield numerous unexpected products. Acyl halides react with alcohols both under acidic or basic conditions. In the absence of bases, the reaction mixture will turn strongly acidic and a number of side reactions can occur, such as the conversion of the starting alcohols into alkyl halides, ethers, or olefins. These side reactions can be prevented by weak bases such as pyridine or DMF. Bases can, however, also bring about the formation of ketenes from the starting acyl halide and thereby of a new set of byproducts. The reactivity of acyl chlorides depends a lot on their structure, as can be seen here. Electron-deficient, sterically undemanding acyl chlorides react with alcohols thousands of times faster than electron-rich benzoyl chlorides, for instance. Still more reactive than acyl chlorides are acyl bromides, and these should therefore be considered when a given alcohol is difficult to acylate. Phosgene is also a powerful electrophile, but chloroformates and carbamoyl halides are usually much less reactive than most acyl halides. On the other hand, the reactivity of alcohols toward acyl chlorides is not as strongly impacted by the alcohol's structure, as shown here. Even sterically crowded alcohols, such as 2-pentanol, react only 50 times more slowly than methanol. This is usually no issue, because acylations with acyl halides are extremely fast reactions and often proceed to completion within minutes, even at low temperature. Let's now have a look at some specific examples. First, at acylations without any bases. In this example, brominated adipoyl chloride was esterified by addition of the chloride to an excess of ethanol. Although the reaction was allowed to proceed overnight, it was probably finished in less than 1 hour. One potential side reaction here was the displacement of bromide by chloride, but this did not occur, despite the long reaction time. Even carbohydrates can be acylated by acyl chlorides without the use of an auxiliary base. In this example, though, the acidic reaction conditions caused the displacement of the anomeric hydroxyl group by chloride. Pyridines are good catalysts for acylation reactions, even under acidic reaction conditions. In this example, a rather unreactive tertiary alcohol was acylated with pivaluyl chloride, also a relatively unreactive acyl chloride. Without any catalyst, even after heating to reflux in toluene for 2 hours, only 32% of ester was obtained. In the presence of 5% of DMAP hydrochloride, however, the yield increased to 95%. To prevent acid-induced side reactions, most acylations with acyl halides are conducted in the presence of weak bases. In this example, a suspension of solid sodium bicarbonate in acetonitrile was used to prepare benzyl bromoacetate. This product is a strong alkylating reagent, but may also undergo benzylic CO bond cleavage by hydrogen bromide. Thus, a weakly nucleophilic base, such as bicarbonate, turned out to be a good choice. Despite their high reactivity, acyl chlorides can sometimes be used to monoacylate diols, as in this example. Usually, when reactions are very fast, derivatizations of polyfunctional compounds yield large quantities of polyderivatized products. This is because the reaction proceeds faster than the mixing of the reagents. To attain a clean monofunctionalization, as in this example, the reaction must proceed much more slowly than the mixing of the reactants. What can be attained by lowering the reaction temperature, by an unpolar solvent, or by choosing less reactive starting materials. Here, the benzoyl chloride chosen was sufficiently unreactive to allow a thorough mixing with the diol, what resulted in a high yield of monoester. As bases, a slight excess of triethylamine and 2% of DMAP were used. Acyl chlorides, such as acetyl or propionyl chloride, react violently even with weak bases, such as pyridine. Nevertheless, high yields of esters are usually obtained when a slight excess of acyl chloride is added dropwise to a cold solution of the alcohol and pyridine in an inert solvent, as in this example. Again, the reaction here was probably finished in less than 1 hour. This example is a highly regioselective monoacylation of the antibiotic chloramphenicol by palmitoyl chloride. The low reaction temperature was critical for achieving this high selectivity. DMF was required to prevent precipitation of the starting materials upon cooling and to provide for a homogeneous reaction mixture and reproducible results. Inorganic carbonates are less expensive and generate less waste than organic bases. But unfortunately, the acylation of alcohols by acyl chlorides in suspensions of inorganic carbonates does not always work. In such instances, the esterification can be catalyzed by organic bases, as shown here. In this example, a mixture of methylimidazole and a tertiary amine was used as catalyst. DMAP instead of methylimidazole could also be used with success. Tertiary alcohols, however, were not acylated under these conditions. Tertiary alcohols can be difficult to acylate, even with acyl chlorides. One strategy is the stoichiometric deprotonation of the alcohol with a polar organometallic reagent, for instance an organolithium or magnesium compound, followed by treatment with the acyl chloride. Metallic sodium cannot be used for preparing tertiary sodium alkoxides because it usually reacts too slowly with tertiary alcohols. This is a further example of the acylation of a tertiary alcohol. Here, a large excess of pyridine was used as base because, as in the previous example, ketene formation was no issue. The esterification probably was complete much earlier than suggested by the 4 days reaction time. In this example, the authors unfortunately did not disclose the reaction time, but a few hours were probably sufficient. Only a slight excess of pyridine was used to keep the reaction mixture from turning strongly acidic without racemizing the acyl chloride. This is again a successful example of the use of an anhydrous suspension of an inorganic carbonate as base. One side reaction observed here was the addition of hydrogen chloride to the alkene, what may indicate that neutralization by the base was not very effective. For such reactions, the particle size of the carbonate and the addition rate of the acyl chloride can be critical for the outcome, and a larger excess of finely milled carbonate may be required to prevent local acidification of the reaction mixture. Enantiomerically pure acyl halides with a high tendency to enolyze, as the one of this example, will readily racemize upon treatment with bases. Nevertheless, if strong bases are avoided, it is possible to perform acylations with such electrophiles, as shown here. Despite the large excess of pyridine, no racemization occurred. With triethylamine, however, some of the acyl chloride racemized. So, what can go wrong during such acylations? Without bases, the reaction mixture will turn strongly acidic, and acid-sensitive starting materials or products may undergo further transformations. For example, alcohols that readily form carbocations under acidic conditions cannot be acylated with acyl chlorides in the absence of bases, because the products are readily transformed into alkyl chlorides or ethers by hydrogen chloride. The second example on this slide shows that a DMF is actually a weak base that can prevent the acid-induced formation of carbocations, despite its ability to stabilize carbocations. A further potential side reaction is the formation of ketene acetals from strongly CH acidic esters, as in this example. Esters devoid of electron withdrawing groups at the alpha position, however, only undergo such acylations at oxygen in the presence of strong bases, such as LDA. If the starting alcohol contains an unprotected carboxyl group, acyl halides can form a mixed anhydride with this carboxyl group. This anhydride can then lead to the formation of unwanted esters. Alternatively, if no bases are used, as in the example on this slide, then the liberated hydrogen halide can catalyze the esterification of the free carboxyl group. One potential side reaction during the acylation of phenols is Friedel-Crafts acylation. These can sometimes occur without any Lewis acid catalysis, as in this example. Electron-rich heteroarenes such as pyrols or furanes may also undergo Friedel-Crafts acylation more readily than expected. Here are a few further examples, but many more have been reported. Most of them were conducted in the presence of pyridine as base, but as mentioned above, for acid-resistant esters the use of a base is not required. The next presentation is about the acylation of alcohols with other acylating reagents, such as anhydrides or imidazolides, and about trans-esterifications. For most alcohols, these less reactive electrophiles are often sufficiently reactive and allow for more selective esterifications. See you then.